Hi everyone. So today we're going to finish up eigenvalue and eigenvector. So I actually don't have too much more I want to show you. What I need to show you would be something like this. So I want to show you why do we talk about eigenvalue and eigenvector. Seems like this pretty strict, pretty restricted to linear function that can be represented by a matrix. Right. Well, guess what? Here's a definitely different ways to look at eigenvalue and eigenvector. Recall from the following. Recall from calculus. For any constant r, d over dt of e to rt is actually equal to r e to rt. Now, if we consider d over dt, the differentiation action, to be called the differential operator, and so let d be the differential operator, and let's say I'm going to let u of t to be e to rt, which e to rt is definitely a continuous function, so therefore e to rt is in the continuous function space. But more importantly, we know that e to rt, the derivative is also a continuous function because the derivative of e to rt is some multiple of e to rt, which is continuous by itself. So therefore, its derivative is also continuous. So therefore, I can now define this. Then notice that d of u of t is just equal to d of e to rt, which is equal to r e to rt, which is equal to r times u of t. Now, if you look at this right here and this right here, that imply d of u of t is equal to r times u of t. That satisfies the eigenvalue and eigenvector. This imply that u of t is an eigenvector. Remember, in this case, the eigenvector, the term vector, mean continuous function, an eigenvector of the differential operator d with corresponding eigenvalue r. So what does that mean? Well, show you. So for example, d of e to 2t is 2 e to 2t. d of e to negative t is equal to negative e to negative t. d of e to the pi t equal to pi e to pi t. Therefore, in these three examples right here, this first one right here, define vector u1, or in this case, I'm going to call it vector u1, but I'm going to call it function u1 of t is e to 2t with the lambda 1 value of 2. And then for this one right here, I call this u2 of t. That will be e to negative t, and then the lambda value is negative 1. And for this last one, I can say u sub 3 of t is e to pi t with the lambda value pi. An interesting thing to note is the following. If I, let's say, want to take a differential operator on a combination of these three eigenvector, I can know that the solution is nothing more than just multiplication of each of these eigenvector by corresponding eigenvalue. Meaning, if I take d of some constant c1 times e to 2t plus some other constant C2 e to negative t plus some other constant C3 e to pi t, I know that the output will simply just be 2 C1 e to 2t. Take C1 e to 2t and multiply by the corresponding eigenvalue, minus C2 e to negative t, plus pi C3 e to the pi t. Now, you might be thinking, okay, so that's pretty neat, and as a matter of fact, I think it should you should find this to be pretty neat because the differential operator is linear and it does have eigenvector and eigenvalue. And the eigenvector is just the exponential function. And the eigenvalue simply be the coefficient in front of the variable. So now the question is, what do we do with all this? Like, how is it useful in what we need to do? Well, because our next section, our next chapter is chapter 10, and we're actually going to start talking about solving differential equation. Maybe I'll give you a little taste of how this works. Eigenvector and eigenvalue, if you actually look on the side, notice that, actually you can't see it because I only record the white part and not the pages, so you cannot see it. But when you're in class and when you see me use the OneNote to go through lesson, you can probably pay attention to what's on the side because it lists all the section. Or if you look at the syllabus, actually I don't know, the syllabus would list each section. Actually, I think it might. You notice that in chapter 12, we actually start to talk about what we call linear system. As in, just differential equation is not challenging enough. Let's just put multiple differential equations together to form a system and try to figure out the solution to that. And one of the methods that we're going to be using to solve a system of differential equation is to use eigenvalue and eigenvector. So I'm going to show you a little kind of idea on how to use it in this example right here. Imagine the following. Let's say we have a we're given a system of differential equation. So the system looks something like this: dx over dy, dx over dt, I'm sorry, is equal to x plus y, and dy over dt is equal to 4x plus y. Now, hopefully some of you noticed what's happening here. Okay, but if not, let's continue. So now, if we let our vector x of t, let's say we let vector x of t be defined to be x of t, y's of t. So that means we define vector x of t as a parametric curve. Then we can say d over dt of, or d vector x over dt, would just simply equal to dx over dt, dy over dt. And if that's the case, I can now rewrite the system that I have here to be the following: d vector x over dt equal to x plus y, 4x plus y. Now here's the interesting thing. If I look at this, I can actually rewrite that into a coefficient matrix multiplied by my variable vector. 1, 1, 4, 1 times xy would equal to x plus y, 4x plus y. And notice that matrix. We have seen that. More interesting is the following. Imagine, instead of talking about d vector x over dt, I'm going to now use a differential operator. And now that means our system of differential equation can be written as this. Or more specifically, Now, how do I solve this system of differential equation? Well, the problem with this differential equation is the following, is that the derivative of x is respect to x and y. Derivative of y is also respect to x and y. So therefore make it very difficult to solve. As a matter of fact, you don't know how to solve that yet. Not until we get to like chapter 12, you won't know how to do it. But I'm going to present a solution using what we do know. What do we know? We do know the following. We do know that this system actually worked out as the following. Let's say let D have two eigenvector. We don't want these two eigenvectors, as I'm going to call it vector u and vector v. Actually, you know what? Maybe, well, we actually do know the two eigenvector and eigenvalue, so let's write them out. So let's take a look so that I remember what are the two eigenvalue. Okay, 1, 2, and 1, -2. So okay, so we do know the following. We know the matrix 1, 1, 4, 1 has two eigenvector, which is vector u1, which is 1, 2, I believe, and then vector u2, which is 1, -2, with corresponding lambda 1, which is 3, and lambda 2, which is -1. So therefore implies the following. So here's the magic, where the magic happened. I cannot solve this system in this form because this tells me that the derivative of x is dependent on both x and y, as well as the derivative of y, which also depends on x and y. But if I now rewrite it using the coordinate uv by letting xy equal to some constant u times vector u1 plus some constant v times vector u2. So basically in this case, I'm using u1, u2 as the basis, and then uv will form the coordinate vector. Based on what we learned, when we use the coordinate vector with the eigenvector as the basis, it will allow me to write out the matrix for the linear function by simply using the eigenvalue along the main diagonal. And therefore, tell me that what we have is this. And because d of uv would equal to the derivative of u, which is u prime, and derivative of v, which is v prime. Now, this system right here is significantly more easy than the other one. Why? Remember, the issue with this system that make it difficult is because the derivative of x dependent not only x, but also y. The derivative of y not only dependent on x, but also dependent on y. So when x and y both changes, then it changes the derivative of dy dt and as well dx dt. This system is a lot easier to do because this system tells me that the derivative of u is only dependent on 3u, only u itself, 3 times it, as a matter of fact. And v is only dependent on negative v. So therefore, this actually transforms into a much easier system to work with. This system of u prime v prime is equal to 3u negative v, change into u prime equal to 3u, v prime equal to negative v, or it changes into du over dt equal to 3u, dv over dt equal to negative v. And hopefully some of you recognize that these two equations can be solved independently as separation of variable. But if you think it that way, you're not wrong, and as a matter of fact, that would definitely allow you to get the answer. But I'm going to ask you to think in another way. What other way? If you think about it, look at this statement right here. Look at these two statements right here. What do these two statements say? du over dv equal to 3v basically say the same thing as d of some vector u equal to 3 times u. And this basically tells me d of v equal to negative v. And if you are looking at this, and some of you might recognize, as a matter of fact, we saw one of these two equations already. This one. Where? Right here. If u is e to the negative t, then when I take the derivative, it becomes negative e to the negative t. Notice this stays an eigenvector of the differential operator with a negative 1 as the eigenvalue, and therefore imply that the solution right here is v equal to e to the negative t. Under the same exact token concept, vector u, I can just say u, or u of t technically speaking, is equal to e to the 3t. You can definitely try separation of variable, and if you do that, you get the same answer, e to the 3t. Oh, well, to be fair, you probably have a constant in front of it. Okay? So, therefore, now I can say this is what the answer is going to be. Our answer in this case would be the following. Notice that u and v are nothing more than just the coordinate vector. To find the actual answer, which is x and y, I can now put in what I know. X and y is equal to u times vector u1 plus v times vector u2. And therefore, I can now define x and y. I'm going to define them vertically to define my two separate functions x and y. We equal to u times 1, 2 plus v times 1, negative 2. And therefore, meaning that xy would equal to e to the 3t times 1, 2 plus e to the negative t times 1, negative 2. And now I can say, well, that would mean x is equal to 1 times e to the 3t plus 1 times e to the negative t. Y would equal to 2 e to the 3t minus 2 e to the negative t. That is my solution. Now I'm going to leave it up to you to actually check the answers. Go ahead and take the derivative of x and y, and then try to see if you take the derivative of x, does the derivative of x equal to just whatever x is plus whatever y is. Take the derivative of y and see if that does equal to 4 times whatever x is plus y. And check that out. If you have issue or not sure how that works, you can ask me in class. Alright, and that actually concludes chapter 3. So, the next video was actually start on chapter 10. We're actually going to talk about solving differential equation. So we finally actually get to some calculus, talk about derivative and integrals and stuff. So hopefully you'll be more familiar with that. Alright, I'll talk to you next time. Okay, bye-bye.